we had been talking about Galois groups. So in particular, we were looking at one we had introduced the Galois group of a polynomial. So the Galois group of F is defined to be X, defined as the Galois group L over K for K splitting field, or for L splitting field. Of F over K. We had proven a number of results about it. Maybe one which turned out to be important is that if we have a Galois extension, then if I take the set all A in L such that phi of A is equal to A for all phi in the Galois group, then this set is actually just equal to K. So the elements which are in the bigger field, which are fixed under all elements in the Galois group, are the elements of the ground field. So I wanted to make a remark, maybe to either confuse you or help not confuse you, that one should distinguish two things. So if L over K is a Galois extension, so then we know that L is a splitting field of a polynomial with coefficients in K. F normal extensions are splitting fields. So we write N to be the degree of the polynomial, and large N of the field extension. Possibly different numbers. So we know the Galois group F, which is the Galois group of L over K, has n elements, where n is the degree of the field extension. For Galois extensions, the degree of the field extension is equal to the number of elements in the Galois group. We proved this the other time. So we can view it in two ways as a subgroup of a symmetric group. First one is the one which one usually uses, which is the most useful one in concrete cases. So note by R the set of all roots of F, or all zeros of F in R. Then the Galois group, then we have seen the Galois group of F is via the restriction to the roots, so via a map which sends an element in the Galois group to R isomorphic to a subgroup of the permutations of the roots. Note that as f has degree small n, we know that the number of roots is at most n. Okay, so this is if we are given, say, polynomial f, this is how we usually study the Algebra group of f. If one wants to concretely study for a concrete polynomial, or in some sense, if one wants to do anything with the Algebra group in concrete cases, once one looks at it as a subgroup, as a subgroup of the symmetric group permuting the roots of the polynomial. The second one we have already also seen is, we know that L over K is a Galois extension, so it's a finite separable extension. So we have a primitive element. A. There is a primitive element A in L, so that means such that we have that L is equal to the extension generated by A of K. So we know that so let's look at the minimal polynomial. Of A over K. Then we know the degree of the minimal polynomial is equal to the degree of the extension, which is large n. And now I can take the roots of this polynomial G, of G. Yeah. We know then this sigma has large n elements, because this is a normal separable extension, so this thing splits into linear factors and has no multiple factors. The Algebra group of F, Algebra group L over K, is the isomorphic subgroup of S symmetric group on sigma, which acts simply transitively on sigma. So this second, we actually will not use so much anymore. We have used it or we have proven it, for instance, to prove that the degree of a Galois extension is equal to the number of elements in the Galois group, because this set says, if it acts simply transitively, that the elements in the Galois group are as many as elements in sigma. But so this is not useful, for instance, to study the Galois group of any given polynomial, but it's useful in some kind of more general proofs, because one is working with a simple extension, and we know a lot about simple extensions. But in concrete cases, one never can use this in a if you're given a polynomial f, you somehow won't find the primitive element, or even if you do, you cannot do very much with it. Okay, I wanted to finish this part on the Galois groups by giving a couple of examples. First, so just looking again at examples that we looked at. So first we had polynomial x to the 3 minus 2. We're looking at the splitting field. So the Galois group of f will be isomorphic to S3, acting on the roots, because if L is a splitting field, of f over q, or whatever, we can describe the splitting field of f over q as L equal to q, the third root of 2 theta, where theta is a, for instance, we can put theta to be e by I divided by 3 if we work in the complex numbers. And so the three roots, so and from this it follows that the degree of L over Q will be equal to 6. Because first we have here the simple algebraic extension giving us the third root of 2, so the degree of that is 3. And theta will not lie in Q third root of 2 because it's complex, but you can easily see that its minimal polynomial is x squared plus x plus 1, so degree 2, and so the degree of the field extension is 6. On the other hand, we know that this must be isomorphic to a subgroup of S3 because of the polynomial is 3. So it follows that the Galois group of F is S3, as acting on the roots. So it's a symmetric group on the 3 roots in the splitting field, it's a symmetric group on third root of 2, theta third root of 2, and theta squared third root of 2. So this is, it permutes these freely, and but that is, so any, okay. So this is how it acts. So if you have any element in this thing, you can write it as an expression in, anyway, I mean, this is what you get. So now the second one we had also looked at was f equal to x to the 4 plus 1. In this case, the claim is that the Galois group of f is isomorphic to C plus. So we had seen in this case, if alpha is a root of this polynomial in an extension of Q, then we can, then F splits F equal to at x minus alpha, x plus alpha, x minus 1 over alpha plus 1 over alpha. And I had claimed that this is irreducible over Q. So Q alpha is a splitting field. Alpha is splitting field of F over Q of degree 4. So we know that the Galois group has 4 elements. And on the other hand, we can see if we send alpha goes to minus alpha, so the map which is identity on Q and sends alpha to minus alpha, and alpha goes to 1 over alpha, this will both give us field, will give us elements in the Galois group. I mean, there are several ways how you can see that these lie in the Galois group, but in particular, you know that the elements in this is a simple algebraic extension. So for every other root, there will be an element sending alpha to any other roots in the of this polynomial, and so these certainly lie there. And okay, and so this describes us. So these you can easily see these commute if you put it in, and so these are both involutions, and so this gives us a group isomorphic to Z2 plus Z2. Okay, so this was this description of the Galois groups, and now I want to come to the next session. I want to talk about the fundamental theorem of Galois theory. Galois theorem. So this will relate say subgroups of the Galois group of L over K so the intermediate fields of the field extension L over K for Galois extensions. Over K. So if you have a Galois extension there, you'll find there is actually a bijection between the subgroups of the Galois group and the intermediate fields. And this is a very important tool to study these field extensions. It's not a magic wand. So it's not like you kind of use this theorem and all of a sudden everything becomes easy, but it is a way how you can start studying things and then use some group theory to study the field extension. So I have to tell you how this correspondence works. So let me give you the two directions. So I have the if I have a subgroup, how do I get an intermediate field? If I have a subgroup of the Galois group. well, good. So L over K is a Galois extension. H subgroup in the Galois group. While the intermediate field, one intermediate field I can get by taking all elements in L which are fixed by every element in H. So the fixed field of H is H set of all elements A in L such that phi of A is equal to A for all phi. These are the elements to which the elements, these are the elements in L, so which the elements in H do nothing. It's easy to see. So of L over K. Now, by definition, every element in the whole Galois group fixes every element in K. And you can see that if two elements are fixed by every phi in H, then also their product and their sum and their difference is, so this will give us a field. And we can also look the other round. So if, more remark, but anyway, so if F is an intermediate field of the Galois extension L over K, how do I associate a group to it? Well, I can take the group of all K automorphisms of all, in some sense, F automorphisms of L. So of all automorphisms of L, which are the identity on K. Then if I take the Galois group of L over F, by definition, set of all phi from L to L automorphism, the restricted to F is the identity on F. This is clearly equal to the set of all phi in the Galois group of L over K, such that phi restricted to F is equal to the F. So this is a subgroup. Subgroup of the Galois. I mean, clearly this is equal because if it's the identity on F, it's the identity on K. So is this subgroup of the Galois group? So in this way, we have associated to every subgroup of the Galois group a certain intermediate field, and to every intermediate field, we have associated a subgroup of the Galois group. Now, the claim is that these two together give us inverse bijections between the subgroups of the Galois group and intermediate fields. So this is the statement of the fundamental theorem of Galois theory. So the maps so maybe I write it like this. We have here the subgroups of the Galva group of L over K. So maybe I first should write, so let L over K be a Galva extension. So the maps, so we have here the subgroups of the Galva group of L over K. Here we have the intermediate fields. Okay. So we have two maps. So for one thing, to a subgroup, we can associate the fixed field. And to the intermediate field F, we can associate the Galva group of L over F. The claim is that these maps are bijections and they are inverse to each other. Really inverse bijections. So what does this explicitly mean? Well, it just means the obvious thing. So if I compose them, I get the identity in both directions. So if I take the fixed field of the Galva group of L over F, where F is an intermediate field, this is F for all intermediate fields. Of the extension L over K. And the other direction is next one. Well, you can obviously the composition as well. So if I take the Galva group of L over the fixed field H for all subgroups of the Galva group. So I mean, although it's clear, I want to stress it again. So the correspondence is that to F, you associate the Galva group of L over F, not something like the Galva group of F over K or whatever. It's always like this. It should be obvious because the Galva group of F, there's no reason it could be the Galva group of F over K, but I say it because almost every year somebody does it the wrong way around in the final exam. So therefore, I warn you, it is like this, and you should remember that it's like that. So the second part is, this is the main part of the theorem. The rest is basically triviality, just some bookkeeping, but I just write it down. So if I take the degree of L over fixed field of some subgroup equal to the number of elements in the subgroup. And if I take the index, if I take the degree of the fixed field of H over K, this is equal to the index of the Galva group of L over K, of H for all subgroups H of the Galva group. And the other way around, if I look at it from the viewpoint, if I start with fields instead, if I have an intermediate field, the degree of L over an intermediate field F is equal to the number of elements in the Galois group of L over F, and the degree of this intermediate field over K is again equal to the index of the Galois group, so in the Galois group of L over K of the Galois group. Okay, so as I said, the last bit is, we'll see, is basically just trivial bookkeeping, but we have to prove the first. So this is for all intermediate fields. F of the extension L over K. Okay, now we will try to prove this. As I said, this mostly serves to try to translate some problems about field theory to problems in group theory, and then hopefully making them more accessible. So we want to show, we will show one. So we have to show, the statement of one are these two identities. The fixed field of the Galois group of L over F is F for every intermediate field, and the Galois group of L over the fixed field of H is H for every subgroup. So we've proved the first one. So let F be an intermediate field of the field extension L over K. So then I claim that L over F is the Galois extension. We have to see it's normal and separable. So we know that L is the splitting field some polynomial say, well, I can still write call it small f over K. And we know if, so because being a splitting field is equivalent to being normal, and so this is over K, and we know if something is a splitting field of F over K, then it's also a splitting field over any intermediate field. So that's also over F. So thus L over F is normal. Now, if we were in, for instance, if we're in characteristic 0, we are done. Otherwise, we have to show it is separable, which is also quite simple. I have my page anywhere. So let say G be the minimal polynomial some element A in L over K. Being separable is equivalent to saying that this minimal polynomial of any element A in L does not have multiple roots in its splitting field. Now, we can also take, say, H be the minimal polynomial the same A over F. Then, so H is we'll divide any polynomial with coefficients in F which vanishes at A. G is one of those, so H divides G. X. So, therefore, as G has no multiple roots, also the factor H of it does not have multiple roots. H has no multiple roots. Splitting. Because G has all the roots of H and possibly some more. And so if there's some multiple roots, I mean with multiplicities, and so if there's if there are multiple roots, then also G has them. So this implies, as I said, that L over F is Galois. And now we can apply the theorem that we proved the last time. We had that for a Galois extension, if we take the fixed field of the whole Galois group, this is the ground field. Now our Galois extension is L over F, and the fixed field is F. So by previous theorem, we have that the Galois group fixed field of the Galois group L over F so this was, so to speak, half of this of the fundamental theorem of Galois theory, and that's why I said that this theorem that we proved before was essentially half of the proof of the fundamental theorem of Galois theory. Now we have to prove this statement, that for every subgroup of the Galois group of L over the fixed field of the subgroup is that subgroup. This we have to prove some stretch, so we will use some tricks, but it's not extremely difficult. For instance, as a tool, the theorem of the primitive element and some other tricks, but it's not very long. So now let H be a subgroup of the Galois group of L over F, L over K. And we have to show if we take the Galois group of L over the fixed field of H. So it is clear, one inclusion is clear. Every element in H, by definition, is the identity on the fixed field of H. So that means every element of H lies in the Galois group of L over the fixed field of H. Thus, it is clear that H is contained in the Galois group L over the fixed field of H. So we only have to prove the other inclusion. And in fact, instead of that, we will just prove that H has as many elements as this group. And so they must be equal. So now we use the theorem of the primitive element. So by the theorem of the primitive element, we can write L equal to K of A for some element A in L. So it's a simple algebra extension. A is our primitive element. Now we write down polynomial, and basically we will be interested, we will want to show that this is a polynomial with coefficients in K, and that its degree is equal, by definition, its degree is equal to the number of elements in H, and that will lead to our conclusion. So we put F to be the following polynomial. This is the product over all elements, say, phi H, x minus phi of A for this primitive element. So this, by definition, is a polynomial with coefficients in Ka, which is the same as L. No, because the entries are from there. And obviously, the degree of F, number of elements in H, no? Because we have as many factors. So first, we note that all the roots of F are distinct. So if H1 of A is equal to phi2 of A for phi1 and phi2, then phi1 2. Why is that? I mean, the field extension is just Ka. So an element in H is an automorphism of Ka, which is the identity on K. If I have two such automorphisms which send A to the same thing, then they must send everything to the same thing. So now our aim is to show, so we want to show that this is a polynomial with coefficients in K. In K. So let's write F equals sum I equal, so over sum I, as many as elements in H, Bi x to the I, so Bi if I are elements in K. And to show F is Kx, which is the same as saying that the Bi are elements in K. So that's actually quite easy to see. So if I take an element psi in H, then I can look at, say, psi star of F, which would just be the sum over all I, psi, where I apply psi to the coefficients. Psi of Bi x to the I. Well, I can also write it. So how do I get this in terms of this? This is the same as if I apply psi each time to the argument here. So this is the same as the product over all phi in H. X minus psi of phi of A. But now, if you see that, it's clear that, if I take all elements in H and I take phi of A, that's the same as if I take all elements in H and take psi of phi of A. It runs through the same elements. So this is just the same as the product over all phi in H, x minus phi of A to F. So that means if I apply, this map, which, so if I apply psi star to it, so if I apply psi to the coefficients of F, I get F. So that means these coefficients lie indeed in K, because they are invariant under the Algebra. No, sorry. So I should correct myself. I want to say they are in Fx. Don't want to. So let me just repeat the last thing, because that's what we want to prove. This is a polynomial with coefficients in F. So these are elements because, so the elements in H are elements in the Galois group of yeah, okay. Okay, let me go back. So what I mean here, so this is the fixed field of H. So polynomial with coefficients with this. So, let me just go through it again as I confused a little bit. So until here, I think it's all clear. We write down this F. This is a polynomial with coefficients in Lx of this degree. And now we can write coefficients like this. And now we can take any element in H. If we apply it to the coefficients of this polynomial, we get the same polynomial back because just of the way this works, which means that the coefficients are invariant under all elements in H. So they lie in the fixed field. So thus, I is equal to all H. So all I also, so thus F is an element fixed field. Okay, so that was the aim, to show it has coefficients in the fixed field. And now we'll see that we are essentially done. So what is there still to do? Now, this is a polynomial which vanishes at A. Now, if you put one element in phi, one element phi in H is the identity of H. And so there is a factor x minus A. So A is a 0 of this thing. So we can compare this polynomial to the minimal polynomial of F of A over this fixed field. So therefore, minimal polynomial of A over this fixed field divides F. No, the minimal polynomial is a coefficient of A over this fixed field, is a polynomial with coefficients in this field, which vanishes at A with the property that it divides any other polynomial with coefficients in the fixed field which vanishes at A, for instance, F. Okay. But now, so as this fixed field contained in L, which is Ka, we have that if I take f of A, if I add A to this fixed field, so for some reason I sometimes wrote f for the fixed field, and now I always do it. If I add A to this will be just the same as Ka. Because the fixed field is contained, and we just add an element which is contained there, so it will be the same. And so, thus, you can look how many elements are there in the Galois group. If I look at the number of elements in the Galois group of L over the fixed field of H, this is the same as the degree of the field extension, because again, this is a Galois extension, because we look, it's an intermediate field. So and now the degree of a simple algebraic extension, f fix h of A over fix h, is equal to the degree of the minimal polynomial. So maybe I give it a name, minimal polynomial. And G divides F. So this is smaller equal to the degree of F, which is equal to the number of elements in H. Now we see that the number of elements in the Galois group of L over the fixed field of H is smaller equal to the number of elements in H. On the other hand, we know that H is contained in this Galois group, so they must be equal. Oh, note I had said here that we have this inclusion. Okay, so this proves the first part, which, as I said, is the main part. Now, let me briefly talk about. I shouldn't maybe. Okay, I leave this here. I can just mark this out because I don't think you remember. So anyway, this is part 2, and we want to prove that. So this is just so let me write f as I did already by mistake sometimes in the fixed field of H for some intermediate field. So we prove the first thing here. So as L over F is a Galois extension, we have that the degree of the field extension is equal to the number of elements in the Galois group. So we get L over F is equal to the number of elements in the Galois group of L over F. And we had just seen that this, F is the fixed field, that this is just the number of elements in H. And so this is the first statement here. And for the second statement, we just use, for this stuff, we just use the obvious things. So other statement follows from the relations that we always have, that L over K, of L over K, is, by the degree theorem, equal to the degree of, say, F over K. times the degree of L over F. Put this together, you get here this second statement. And the second formula is basically, the second part is essentially precisely the same. Anyway, I can also, one more minute, read. So if I have an intermediate field, so now F intermediate field. Okay. Then we have again that L over F is equal to the number of elements in the Galois group of L over F. So that's basically just, we know that because it's the Galois extension, and then the rest follows again. By this relation. Okay, so that's the proof. So you can see it's a little bit tricky, but not super difficult. We have done more difficult things before. And, but now we have this correspondence between this projection between the subgroups of the Galois group of a Galois extension and intermediate fields. So once one has this, one can ask a number of questions. So one question you could ask yourself, so there are some subgroups are nicer than others. You could have, for instance, normal subgroups. What kind of field extensions, intermediate fields, will correspond to normal subgroups? Do they have some special property? Or you could also ask another question. There are some intermediate fields which are nicer than others. So you can look at an intermediate field such that the intermediate field over the ground field is itself a normal extension. What kind of subgroups correspond to that? And now, as the name suggests, two things correspond. So normal is equal to normal. And obviously, that's not a coincidence, but it's called like that because of that. So normal subgroups of the Galois group will correspond to the intermediate fields which are normal over the ground field. So now I want to prove this. So to show L over K E Galois extension so we have that H subset the Galois group L over K normal as a subgroup if and only if I take the fixed field of H over K. This is the normal extension. Note that, we know that if we have a Galois extension, then the bigger field over any intermediate field is a normal extension, because it's the splitting field of the same polynomial over the intermediate field as L was over the ground field. But now we ask that it's normal over the ground field. So that's a very different question, and that's an actual condition. And so that corresponds to the subgroup of the Galois group being normal. So now we want to prove this. So first we will prove a little bit more. So maybe we can also understand a bit more. So we can anyway ask ourselves, if we have an element in a Galois group, how does it move around the intermediate fields? So let F, so we assume still we have this Galois extension, let F be an intermediate field of the Galois extension L over K, and let alpha be an element in the Galois group. So we can look at the following. We write alpha of L. Well, this is just the set of all alpha of A with A, not L, in F, of A in F. Okay. So we just can apply our element in the Galois group to any element in the intermediate field. Now, you can see if you apply alpha to a sum, you get the sum of the alpha of the thing. If you apply it to a product, you get the product, or for the difference or the quotient. So alpha of F is an intermediate field of L over K. Alpha of L of F of extension L over K. It also contains K because alpha restricted to K is the identity, so it certainly contains K. So that means if you have that in a certain sense, so you could say that the Galois group of L over K operates on the intermediate fields. It moves them around. And now, how one can ask, so the first thing is what happens to the Galois group if I replace alpha by F by alpha F, and the claim is it gets conjugated. And this, so let L over K is still a Galois extension, and F is still an intermediate field. And alpha is an element in the Galois group. Small one, then if I take the Galois group of L over this intermediate field, this is alpha times the Galois group of L over F times alpha to the minus 1. So it's obtained from the other Galois group by conjugation. So it's a conjugate subgroup of the other Galois group. And this is actually essentially trivial, just by definition. Just write it down. So let's take any element in the Galois group. Okay. So when is such an element in this Galois group of L over alpha F? Well, obviously, if it leaves every element of alpha of F fixed, so this is if and only if for all A in F, we have that if I apply phi to alpha of A, this is equal to alpha of A. Now we can multiply here by alpha to the minus 1. So this is equivalent to saying for all A in F, we have alpha to the minus 1 alpha of A is equal to A. So which is the same as saying that alpha to the minus 1 phi alpha is in the Galois group of L over F. And obviously, by multiplying now back with alpha on this side, alpha to the -1 on the other side, this is equivalent to phi is an element in the Galois group of is an element in alpha Galois group of L over F, alpha to the -1. Okay, so this is just by definition, we have this happens to the Galois group when we act on the intermediate fields with alpha. And now we want to prove our result about normal subgroups versus normal intermediate fields. So the following theorem. So we have let L extension. And F an intermediate field. The following are equivalent. First, F is normal over the ground field. Second is that if I apply alpha to F, then this is equal to F for all alpha in the whole Galois group. No, so I'm not saying that every element of alpha of F is sent to itself. No, it's just alpha is a bijection of F to itself. It doesn't map it to another field. And the third one is that the Galois group of L over F is a normal subgroup of the Galois group of L over K. Okay, so let's try to prove it. So we have to, it's always, it's not a triviality, some effort we must do. So we have to do all the directions. So we first do 1, 2. So we have to show, so we assume that F over K is normal. And we want to show that this is true. So we take an element A in F. We have to show that alpha of A also lies in F. So maybe, so let F be the minimal polynomial, small f be the minimal polynomial of A over K. So as F is normal over K, all its roots lie in F. Of small f lie in the field large F. On the other hand, we know, we know that the Galois group will send roots. So let alpha an element in the Galois group L over K. Then, by the trick we have used about a dozen times so far, alpha of A is also a root of polynomial f, because we have the usual thing. If we take f of alpha of A, because the coefficients of f lie in K, it doesn't do anything to f, and we had seen that this implies that this is equal to alpha of f of A equal to 0. So, but all the roots of f lie in f, so thus also alpha of A is an element in f, because it's a root of the polynomial f. So this implies that alpha of the field f is contained in f, and applying the same argument. So alpha to the minus 1 gives alpha to the minus 1 of f contained in f. So if I apply then alpha to this, this means alpha f is equal to f. So this gives the other inclusion that f is contained in alpha f if I apply alpha to it. Okay, so this was the first part. This was not very difficult, but we have to use again this trick, and we have to somehow use the story with the minimal polynomial. So it's not. So now 2 to 3, I think, is quite simple, because that's we basically already proved. So let's see. Where is it? Yeah. So we assume 2. So assume alpha of f is equal to f for all alpha in the Galois group L over K. So, so we take some alpha in the Galois group. But then we can just write it down. If we take alpha, the Galois group of L over K, alpha to the minus 1, L over F, sorry, then this is the Galois group of L over alpha of F. By the lemma. But alpha f is equal to f for all alpha in the Galois group, so this is just the Galois group of L over f. So for all alpha in the Galois group of L over K, if we conjugate with alpha, we get this group again, so that means it's a normal subgroup. Normal subgroup. Okay, so that was that, and now the last part is a little bit slightly more tricky. We have to actually use the fundamental theorem of Galois theory to go back. And in some sense, so we go from 3 to 1, but actually what we do is we go from 3 to 2, and then from 2 to 1. But we just, because we don't have a shortcut. So 3, 1. We assume that the Galois group L over F for some intermediate field is a normal subgroup. of the Galois group of L over K. So then we know that the Galois group of L over F equal to alpha, the Galois group. So if I take any alpha in the Galois group, L over K, if I conjugate with it, then we know this is the Galois group of L over alpha of F. So the Galois group of L over F is equal to the Galois group of L over alpha of F. But remember that the fundamental theorem of Galois theory says that the map which associates to an intermediate field, the Galois group of L over it, is a bijection. So that means if these two Galois groups are equal, then the intermediate fields are equal. So by the fundamental theorem of Galois theory, we have that F alpha of F. So we have managed to go back to 2. And now we have to do the last bit. Now we want to show that F over K is normal. So that means we have to take, have to show if you have an irreducible polynomial with coefficients in F, which has a root in L, then it splits over L. No, if it have an irreducible polynomial in with coefficients in K with a root in F, then it splits over F. So let F in X be irreducible with K in F. You have to show it splits. In the field large F. So let's take another root. Let B another root of F in L. We know that L over K is normal. So F therefore splits over L. So both A and B have the same minimal polynomial over K. Namely our F. So therefore, we know if two polynomials, if two elements in the larger field have the same minimal polynomial, there exists an element in the Galois group which sends one to the other. So therefore, element alpha in the Galois group of L over K tends A to B. So thus alpha of A, and A was an F. Thus B equal to alpha of A is an element of alpha of F, which was F. And so therefore, our polynomial, original polynomial F, small f splits over F. Over the field large F. So it's a normal extension. Okay. Now we can also ask us something else. So now we have this, this statement that if we have a normal subgroup of the Galois group, we get that the corresponding intermediate field is normal over the ground field. So then a natural question would be, what is the Galois group of F over K? Can you describe it in terms of the other stuff you are given? Now you have the Galois group of L over K, and you have this normal subgroup. So the natural reaction would be that you divide the Galois group of L over K by this normal subgroup, and you hope that this is the Galois group of this, and this is indeed the case. So this is the following corollary. That L over K, the Galois extension let F over K field which is normal over K. Then the Galois group of F over K is isomorphic to the Galois group of L over K divided by the Galois group of L over F. Okay. And that's in some sense an exercise. One just has to see what one is looking at. So the point that we use is the elements in the Galois group of L over K send F to itself. So they themselves will give us automorphisms of F. So let alpha be an element in the Galois group of L over K. Then we know by this theorem that alpha of F is equal to F. So thus, if we restrict alpha to F, so this is now, this is a map from F to F. It starts, it's a restriction of an element in the Galois group here, so it's an identity on K. So it's a K automorphism of F. So this is an element in the Galois group F over K. So we get just by restriction this. And so we therefore have a homomorphism. We have the restriction homomorphism I could call restriction F from the Galois group of L over K. So Galois group F over K extends element alpha to alpha restricted to F. So this is clearly if a homomorphism of groups. Oh, the composition of two such elements in the Galois group corresponds to the composition here. Fiction obviously commute with each other. And what is the kernel of this map? When does an element act on the Galois, act as the identity on F? Well, if and only if it lies in the Galois group of L over F. So with kernel. Galois group. Because by definition, the Galois group of L over F consists of all elements in the Galois group of L over K, which act as the identity on F. So that's precisely the definition of the kernel. So thus we have a homomorphism, so thus get an injective homomorphism from this quotient, the Galois group of L over K divided by the Galois group of L over F. So the Galois group L over K, just sending equivalence class of alpha modulo this to the restriction of the thing to F. But now I claim these have the same number of elements. We know that how many elements does this thing have? Take the Galois group of L over K divided by the Galois group L over F. So this is precisely equal to the degree of the field extension L over K divided by the degree of the field extension L over F, which is the same as the degree of the field extension K, which as F over K is now also a Galois extension, is equal to the number of elements in the Galois group of F over K. So we have an injective homomorphism from this quotient to here. On the other hand, the number of elements are the same, so it's an isomorphism. Thus, it's an isomorphism. Okay. Yeah, I wanted to still do a couple of examples before I finish this, but maybe it's more reasonable if I do them the next time. So I will stop here. Are there questions? Okay. So then, thank you very much. We will, I guess we see each other again on Friday. I wish you success for your exam in real analysis on Thursday, no? And have a good evening. Okay, I hope somebody still hears me. Okay, bye.